everyone. Thanks for joining this session on computer vision coming to a store near you. My name is Brent Biddulph, Managing Director of Retail and Consumer Goods for Cloudera, and I'm joined by my friend and colleague, Florian Muller-Klein of Miner and Cash. So today, what we want to talk about were industry trends in retail, specifically in-store retail. What are the business drivers that really make computer vision a valid approach and a need, frankly, for addressing key industry challenges? Some use cases, some illustrative examples of what retailers are doing today. Also, some nascent applications of computer vision in retail. How it works and bringing it all together. So why are we talking about in-store retail when all the buzz and excitement is about e-commerce, digital? Well, because 86% of retail sales are actually done in store, will be done in store in a few years. Today, it's actually more than 90%. So for traditional retailers, brick and mortar are not only critically important to the business, they're foundational, and ultimately, they can be key competitive differentiators versus the digital disruptors. So in-store retail is critically important. Not talked about a whole lot, although we're seeing a lot more stories in press in terms of how retailers are moving forward, and those are some of the stories I wanted to share with you all today. So what's making it exciting from an in-store experience? Well, IoT and the edge, as we talk about, they've been around for a long time in retail, from basic sensors. But what really is starting to grow now, beyond just basic sensors and beacons we heard about a few years ago, is streaming video. And applications leveraging computer vision include satellite images, taking photos of parking lots, understanding traffic outside of stores or your competitors, magic mirrors, which you've probably heard about to some extent in high fashion, being able to try on clothing, styles, colors at the swipe of a finger versus actually having to try on outfits repeatedly. Frictionless checkout, so the ability to check out without actually having to talk to a cashier and go through the whole process of traditional checkout, as well as autonomous vehicles in retail. We're seeing retailers experiment not only with autonomous vehicles from a delivery standpoint, but also even autonomous stores. Can actually go to what we call food deserts in retail, where you have high-density urban areas. There may not be a local grocery store to be able to provide food. We're seeing retailers now starting to experiment with actually pushing autonomous vehicles loaded with a small assortment of goods for consumers to actually be able to purchase on the fly. So why is computer vision critically important going forward in retail, and how are these applications starting to take hold? As McKinsey stated, for AI and IoT specifically in retail, a low-end estimate is about a $410 billion economic value add overall from IoT, and they expect within that a large component to be computer vision driven, and ultimately that being streaming analytics and also more real-time in terms of capabilities. So what does computer vision bring? Well, it brings real-time processing, improved accuracy. If you think about it, what you can actually see going on in a store versus trying to interpret data without actually visually seeing gestures or moods or physical products, how they stand at a moment in time. Really only computer vision can provide those insights. And then deeper insights about consumers. So, loyalty programs aren't pervasive in retail. Not every retailer has a loyalty program. Not every retailer knows every individual when they're in the store, when they walk in, how they shop. But they certainly can start to augment information about consumers through traffic and demographics, understanding gender, age, those kind of things, leveraging computer vision to kind of get a better sense of day part shopping from a demographic profile standpoint. Oh, and just want to, really the four key areas within computer vision that are really starting to take hold in terms of business impact are around enabling that frictionless commerce, improving operational efficiencies, improving customer experiences, and reducing fraud and shrink. So those are all critical areas within retail overall that computer vision can help. So we're probably all familiar with the Amazon Go store, a lot of hubbub last year when it opened up. It's a small 1,800-foot convenience store for all intents and purposes. Products are highly curated in slots, but the entire store is run on computer vision and sensor fusion with deep learning capabilities. So what does that mean? As a consumer, you basically walk up with your mobile device, through your Prime account, you scan a QR code, you walk in, computer vision is picking up where you are in the store physically, products that you're picking up or even putting back, As you check out, you essentially just walk out. There is no checkout. So it hits your Prime account usually within about 3 to 4 minutes. You'll get a bill, or it'll be your receipt effectively. So pushing the edge in retail. Now, that didn't happen overnight. They spent about 2 years testing it. 1 year after the 2 years of building it, that is, 1 year with their own employees, and they finally rolled it out last year. So it was a 3.5-year POC with a lot of heavy lifting to build that out. But what it illustrates is the capability and the opportunity moving forward in reshaping the future of what stores will look like in the future from a frictionless checkout standpoint. Another example is Alibaba. So in China, they can even take it to the next level where consumers can actually check out with their face. In China, it's well accepted. It's a cashless society. Facial recognition is widely accepted, unlike the West. So being able to apply that in China is certainly something that, in the West we go, no, you can't go there. They already are, and they're testing it in 100 stores that they have rolled out, which are primarily grocery stores, and it's a fully automated environment. In fact, there was a talk just earlier today from Alibaba about how they've infused, digital and physical really is this test within this particular format. But from a computer vision standpoint, the key aspect here is the ability to just check out with your face. You don't even need a phone. In terms of improving operational efficiencies, this has also been in POC here in North America with several retailers. Just in the last 2 months, 2 majors here on the East Coast, as well as nationwide with a major remodel that was announced. We're going to be seeing robots in stores. So why robots in stores? It seems a little fanciful, but from an operational standpoint, being able to capture physical product locations, especially in fast-moving consumable goods, understanding adjacencies, are the prices correct, are there out-of-stocks we need to address? That merchandising compliance component has huge potential and ROI to resolve. It's a challenge that's existed in fast-moving consumable goods for a long time. So these robots are armed with cameras all around. They cruise up and down the aisles. They can cover, I think it's a 60,000 square foot store 3 times in a day. So it can cruise up and down an aisle within just a couple of minutes. So these are actually being rolled out now. So we're going to start to see them at least in fast-moving consumable goods in a couple of the leading providers. So the key benefit here is out-of-stock compliance. Out-of-stocks are a huge issue in fast-moving consumable goods. Anywhere from 9 to 16% of grocery stores or mass merchants are out of stock on product. And it's a multi-billion-dollar issue that's been around. Demand forecasting has been trying to solve this issue. What it really comes down to is store execution. It isn't that the product hasn't been shipped to the store. The biggest challenge is just notifying store employees or associates that, hey, we've got an out-of-stock to deal with. We need to take it from the overhead or the back room and fill the shelf. Out-of-stocks are very costly. Recent research actually kind of brings this home. So this is a challenge that's existed in retail for a couple of decades. But now what's happening with consumers is they shop the store, they're not able to pick up that one item. Not only are they frustrated, but now they can very, very easily fulfill that just dialing up Amazon and have it delivered to their home. So now that challenge in retail has kind of come home to roost and not being able to address that. Now it's directly feeding a 24% revenue line for Amazon. So it's critically important to be able to address out of stocks, and through computer vision, whether it's leveraging robots or in some cases ESLs, electronic shelf labels with built-in cameras, being able to identify those out of stocks at the moment of truth, to be able to then provide that information back to the store associates to basically go address that out of stock. But the other side of this equation, whether it's an ESL or a robot, is merchandising compliance. There's huge amounts of promotional money that's spent between CPG and fast-moving consumable goods retailers just around shelf compliance. So not only do retailers want the right products in the right location with the right adjacencies, the right promotions, prices, all those things going on, the right items on display, there's a huge incentive to make sure that that's all right, because they're ultimately, in many cases, being paid by CPG, for shelf space, for display space in individual stores. And that information today typically comes through third-party providers. It's typically just sample information. It's not really a pure sense of what's going on in an individual store. So it's, the merchandising compliance standpoint is also a critical aspect of being able to capture this information, leveraging computer vision. And to that point, CPG on an annual basis spends about $175 billion with fast-moving consumable goods companies. Now that includes TV advertising, weekly ads, but it also includes shelf compliance, promo tags, displays, and of that, $174 billion, only 17% is allocated towards the shelf, when in fact, as IRI has stated here, 68% of decisions typically are made at the shelf, so it's kind of an upside-down world. And why is that? Because the information can't be provided back to be able to justify that spend, to be able to reallocate that money all the way back down to the retailer to where you can really make a difference. So improving customer experiences. Now this is very nascent right now, and this isn't facial recognition, this isn't like, creepy stuff. This is basically just understanding consumers that are either happy, unhappy, and understanding their gender, and an opportunity to engage consumers as they come into the stores or shop in the aisle. So if someone's unhappy, that can be noticed through computer vision identification in terms of mood. Being able to then have a proactive customer service desk person or someone in the store to be able to proactively engage that customer to make sure they're having a better experience, or be able to prompt them and interact with them. We all know, we all go into retail, it's hard to find people. But if we can at least address those that are unhappy and try to turn that smile upside down, it's a huge area of opportunity. It's very experimental right now, but it's, there's already cameras in stores today. So it's not like physical infrastructure is going to be highly expensive. It might just be a matter of relocating or repurposing the use of that information. And of course, magic mirrors have been around for a while. Neiman Marcus, has talked about this. Others have been applying it. It has a real practical application, especially in apparel and beauty, where consumers can actually, try on a fit, physically try it on, and then just change color, style, pattern very easily. It helps move through the whole, trying on outfits is not pleasant for men or women, right? So being able to make that a faster experience is all enabled by computer vision. The same thing on the beauty side. When you want to test makeup, color, styles, you can capture, save that information, and provide it back to the consumer. The real interesting aspect of this now, returns in apparel aren't as heavy as they are on online. Returns in retail online are a really big problem. And online retail right now, and everyone's experienced, even Amazon's not immune to this. A lot of consumers in apparel, they'll buy 3 sizes, they'll keep 1 and send 2 back, right? So there's a huge cost when it comes down to apparel. So anything you can do, even in store, there's still a lot of return issues. Anything you can do to kind of improve that fit versus just a size, because we all know different brands have different size. So what people are really moving into in retail right now is helping to identify better fit, better overall experience in terms of apparel and in high-end fashion. So that's just kind of a flavor of how retailers are applying it today. It's no longer a future store of the future. It's actually here today, but it is relatively new. You can, in fact, you probably are in a store near you that's leveraging computer vision in some way, shape, or form. We are on the verge, but it's kind of at the tipping point where it's going to continue to drive, and there's many reasons for that from a business implication standpoint. Other examples, there are shopping carts that are out there that actually have cameras built into them, sensor fusion, same idea of just loading product. It already knows what it is. You basically bag it yourself and take it out the door. You don't need to check out right there on the shopping cart. Consumer insights, so even leveraging computer vision from just a gesture standpoint, this basically is how the Amazon Go store works in terms of understanding if you're pulling a product off the shelf, if you're putting a product back, being able to understand that gesture. Customer engagement, so not only understanding, gender, age, but also distinguishing between a shopper and an employee. So in consumer electronics, high-end fashion, where you tend to want to have more of a VIP experience, you want your associates to engage customers, unlike a grocery store, for example. You want that engagement, so now you can start to be able to score your own employees. Are they engaging customers that are walking in, and understanding that dynamic between gender and age and the store associates. So applications, certainly in consumer electronics or high-end fashion there. We already talked about ESLs. There's the mobile, now it's very experimental, the mobile grocery store. And also the satellite imagery. This is something actually that I just learned about earlier this year at Shop Talk. There's actually companies and providers out there that are capturing satellite imagery of parking lots, not only of your store, but your competitors, and understanding traffic in terms of times, intraday snapshots, if you will, in terms of what traffic or opportunity do you have versus what's going on at a competitor. So again, another use of computer vision in retail. And of course, loss prevention. That's kind of where computer vision really has had its roots. That continues to, advance, if you will. A lot of experimentation there with facial recognition. So if someone has a criminal record or shoplifted in your store before, you actually have a mugshot, you can match. But that's a very delicate area, and while there's been experimentation, I think retailers, at least in the West, are backing off of that a little bit and trying to go to more anonymous type gesture analysis in terms of fraud and shrink. So with that, hope that gets you a little bit of a flavor of what's going on in retail with computer vision and AI. As we talk about edge to AI, this is the whole shebang, if you will, in terms of the implications within retail. With that, I'll turn it over to Florian to kind of how it works and bringing it all together.
All right, cool. So I'm going to talk a little bit about how this stuff works and how you can implement it in your own store. What we're going to end up doing by the end of this is we're actually going to build an example use case and actually see all the moving parts and everything. So I'll try to speak up until the microphone comes on. So by the end of this section here, what we're going to have is we're going to have an actual working demo of something that you can implement into a store. So what we're going to do is we're going to take, it's going to be for a fashion use case, right? So whether this augments a magic mirror or whether this is some tool that you have in the store to help some customer find a piece of clothing that they're interested, or find some style that's similar to some example that they may bring into the store. So we're going to detect that clothing, we're going to compare it to our inventory, and then we're going to make a match to actually point that customer to the inventory in the store. Your options for implementing this in your own store, you can purchase a point solution for one of the moving parts in one of these systems. So typically when you see what we call an AI system implemented, there's a lot of moving parts, right? So some of those parts are going to be a machine learning model. Some of those parts might be some logical algorithm that kind of interprets the model or the data coming in. And there's a lot of providers out there that can sort of, give you one of those pieces of that entire AI solution, as one chunk. You could hire a company to design and implement a custom solution for you. So that's a shameless plug for my company. We do that. Or you can implement the solutions yourself. So what I'm going to talk about is how we would design a computer vision solution for some problem that you may have. So what you want to do is, like I said earlier, a lot of these AI solutions are essentially a lot of different components all pieced together, right? So when you have a computer vision problem, you want to break it down into its smaller constituent parts, right? So within computer vision, there's a couple of different what I'll call modalities. And these are the things that a machine learning model is good at doing with some image, right? So given some image, there's some type of model there that can produce a specific type of output on that image, right? And whether or not that's the entire solution that you're looking for is going to be dependent on the problem. So the machine learning system might just be a small piece of the entire kind of AI pipeline that you're implementing, or it could solve the problem that you're looking for directly. So we're going to get into a little bit more details of all those things in the next couple slides. But oftentimes, the machine learning component is just one component within some computer vision solution. And we may have multiple of those computer vision modalities within one problem. So the example that we're going to end up building at the end has a couple of these modalities within a single problem. So we'll see how all of these models can fit together to actually make a solution. So if you are going to end up with a machine learning method within your computer vision problem, you're going to need to develop some methods for feeding data into the models. You're going to need to develop some methods for interpreting the output of those models into something that's actually actionable for either you or your customers, because the model output is going to be something mathematical, most likely, and that's not directly sort of actionable for what you're looking for. And we'll need a system to chain all these things together, and then we'll need to translate from model output to something that's human interpretable. All right, so machine learning and computer vision. So when we talk about machine learning and computer vision, we're often talking about deep learning. So deep learning is essentially, when you hear deep learning, you think of neural networks, right? So neural networks have driven a lot of recent success in computer vision. So this is one of the areas where machine learning is really shown to be extremely successful. So we're going to focus most of our focus on the deep learning models when we talk about machine learning and computer vision. So essentially, it's a specific type of neural network that's designed to exploit the spatial nature of image data, right? And the models are nice to use because they're, we can think about them as being sort of modular or flexible in the sort of input-output schemes that we're looking for. So I'll go through a couple examples here. Previously, when I talked about the computer vision modalities, what we're thinking about is the different ways that we want to produce some output on an image, right? So whether we're trying to make a global inference over the entire image, whether we want to have our inference be spatially aware, right? So think about like if you want to identify where something is missing on a shelf, you want to know that something's missing, but also exactly where the missing the empty spot is, right? Or if you're trying to track movement throughout your store or something like that, you want to sort of end up with a heat map of you know, like where is the most traffic and the least traffic and things like that. So you want the output to be spatially aware. Or we might want to make our output as fine-grained as possible down to the actual pixel level, right? So you know, an image is basically a bunch of pixels, and we want our output to map exactly pixel to pixel from the input. Or we just want to do, you know, what us data scientists call is learning latent representations of the image. And what that means is we're just sort of coming up with a good representation of the image that we can perform math on so that we can make some sophisticated inferences on that image. Because you can't, you won't be able to do some of these inferences on raw image data, but you can on some intermediate representation of that image. And deep learning models can do all of these things. So if we want to make some global inference on an image, let's say we wanted to, you know, sort of look at one of our customers in a store, and we wanted to know their gender, affect, if they're wearing glasses or headwear or something like that, right? So we would take in an image and we would produce an output to a certain category or a certain bucket, you know, from that. So this is a global inference, right? So we can't really segment this image into its finer parts, but we can tell you a couple of like high-level facts about this image, right? So we're using the same sort of backbone structure of the neural network. We're just changing the way that it's generating the output. For spatially aware inference, we might want to do something like this. Like we're finding all of the people in the store. We're saying, you know, what is their gender, and we're estimating their age. So here, we're making a classification for every single you know, person that we found within the image, right? So what this neural network here will do is it will produce, you know, classifications. So this would be male, female, an age guess, and then bounding boxes or locations within the image, right? So we're actually spitting out classification and a location for every single one of those individuals in this image here. Or if you wanted to locate products on the shelves or something like that, like I mentioned earlier. So pixel level inference. So this sort of takes the spatially aware inference and just kind of like kicks it up to another level in terms of how fine-grained our output is. So what we would want to do here is we're taking some image in, and then we're classifying every single pixel as to what object that pixel is a part of. Or we can sort of produce a probability map over the entire image. So this is like where an individual is likely to be, or where, you know, the sort of these people are sort of traveling throughout the image. You know, if it's an image, if it's an overhead image of a room, right? Okay, and then learning latent representations. Essentially, we're going to push an image through the neural network, and then what we're going to get out of that is a representation of that image that we can perform math on. All right, so given those sort of building blocks, how can we put them together to actually make something useful that Brent showed us in the beginning? So let's assume that we're going to develop a tool to help our customers find an article of clothing. So let's assume that we're a clothing retailer, right? And we want to build something that sort of helps them interact with our inventory and kind of search it more efficiently in a way that is more similar to how you would kind of look at clothing and decide what's a style that you like and what's a style that you're looking for in that sort of like abstract kind of style search space, right? So let's say they come into our store looking for a specific article of clothing. Maybe they have an image of that article of clothing with them. Maybe they're wearing it and they want to find something similar. Or maybe they are using a magic mirror and they kind of they pick a few things that they like in your inventory and they kind of want to augment that with things that might be similar, right? So what we want is we want something that can take in an image. We can separate out all of the articles of clothing within that image. And then we want to do a sort of semantic level search. And when I say semantic search, I mean more like the stylistic characteristics of some article of clothing, right? And actually match all of those articles of clothing, right? So we have a lot of moving parts here. So what we're going to end up with is we're going to end up with 2 machine learning models and then some algorithms or logic to kind of glue all of those together, right? So what we're going to do first is we're going to use a pixel level segmentation model. So what we're going to do is we're going to take in an image, and then we're going to produce a sort of mapping as to what pixel represents which article of clothing. So hopefully it's easy to see on the screen here, but actually for this image here, every article of clothing is a slightly different shade. So the coat is like a darker blue than the dress or the pants, and then the shoes, and then the hair and the sunglasses, right? So the model has sort of taken the image and sort of segmented out all of the pixels that represent the different articles of clothing. So that's model number 1. Model number 2, we need some way to take that extracted article of clothing and then put it into some mathematical space that we can then search through to quickly generate those matches that I was talking about earlier, right? So here, this big blob of images, I basically downloaded a bunch of clothing images from the internet, and I'm assuming that those are that's my catalog or my inventory of images in my store, and then I sorted them in this high-dimensional space using a neural network. So if you were to zoom in on any one of these, they're all sort of similar articles of clothing. So down here are all blazers. Over here is, they're all plaid like shirts. I call it like Plaid Island over here. And things like that, right? So the neural network has kind of organized our inventory based off of their stylistic qualities. So we're going to take in an image. We're going to apply a filter to that image based off of the results of the segmentation model and what article of clothing we're looking for. So in this case, we're looking for a coat. So we're going to essentially only save the pixels that are making up that coat that their neural network decided. So the neural network produces this output. We know one of the colors represents coat, so we're only going to take the pixels from the original image that are from the coat, right? We're going to push that coat through the representation network and sort of get the latent representation of that coat, and then we're going to match it to our catalog and find the best match in our inventory, okay? So if you're familiar with this equation here, it's basically just a mathematical function to calculate the distance between any 2 vectors. So that's essentially what we're doing. I'm going to gloss over those technical details here. So what we get is we get an original image, we extract what we're looking for, and we find the closest match in our catalog, right? So we can actually watch this. So I actually built this using some public data on the internet, just to show you that this is actually concrete things that we can put together. So here what we're going to do is we're going to say we're looking for a coat. We're going to select the image that we're looking for, and then we're going to search our catalog. So this is going to take a couple seconds because I ran it on a laptop, not actually like a powerful sort of server setup, right? So we'll just give this a couple seconds here. So what happens is it pulled out the coat from this query image, and then it searched through that fake catalog that I made, and it found me the match that it thinks is the closest stylistically to the coat that we're looking for. So if you think about sort of building tools to kind of augment the sort of search space in your retail space. Computer vision can be very helpful, for something like this, where they kind of, keyword searches it may be hard to capture like what is stylistic, like what is specifically stylistic about this article of clothing versus this other article of clothing. So bringing it all together, if you were to sort of inject machine learning or computer vision capabilities into your infrastructure, it may look something like this, where you have the data coming in, the data engineering part here sort of has this cyclical aspect to it, because when we're generating new representations of our data with a machine learning model, we want to sort of generate those for our catalog that we have and new data coming in, and then we want to store that back into the database, right? We can kind of augment all of our sort of data warehousing and information that we store with every single piece of inventory with the information coming out of the machine learning models. So with that, we're all done here. So if you wanted to reach out to either of us, our contact information is there. So thank you.
Also, I think we left a little room. If there's any questions in the room, feel free to ask. Yeah.
Yep. You had said that this is part of the present, it's no longer the future. So I was wondering, for example, in the case of grocery stores, is there one cloud vision technology which many of them use, which has become standard in the industry? Like the most frequent, the most common?
Yeah. I have thoughts about this.
I would say there is no one standard. There's definitely not a standard. And what's happening right now is like like Bossa Nova, who makes robots to cruise up and down the aisles, right? There's 4 other Bossa Novas that also make those types of devices. So they tend to bring along their own black box. So if they want a plug-and-play solution, they can help facilitate that. It really depends on if the retailer wants to own the IP and has the competency to do it, they're going to do it, right? And they may leverage that from a technical delivery vehicle, but black boxes are kind of like, traditional data warehouses of the past. People are building up competencies, skills, and they really see that as their IP. So I see a mix, personally, in dealing with grocers around the world. Either they want to get started and they test a vendor solution from a POC standpoint, and then they start negotiating with the vendor on, hey, we've already got a staff who can build this. We don't want to pay all this extra for the AI, so there's a negotiation that might happen there. For those that don't have the budget, don't have the skill sets, they may just go with an easy button. But more than likely, they're probably not going to invest in this type of technology. They got bigger problems, right? If they can't invest in the skill sets and the technology to do that, they probably have other issues to deal with. So it's all over the board. It's going to depend on level of maturity, skill sets, how they're investing. Are they an analytically driven company? In many cases, they aren't. As we see in real estate, or in retail rather, retailers are failing. Why are they failing? Because they're not investing in skill sets and technology. They're totally sunk in, with real estate, right? They're fully leveraged through private equity firms that provides wraps around them that they can't make those investments. So, the retail apocalypse, is kind of ridiculous. It's more like a thinning of the herd. And in North America, there's more retail space by 3 or 4x than anywhere else in the world, so we were already overspaced as a country. So, and it's a long-winded answer, but it's kind of like all over, and it's very much in test.
And I can add real quick, to add to the already long answer. Certain problems are going to lend itself better to these kind of off-the-shelf solutions like you're asking about, and certain problems are going to require a custom solution. So, something like grocery, the objects, that you would sort of be pushing through some of these models may be generic enough that it could be, effective. But for this particular example, it was only successful because the model was custom trained on the data set that it was, because different retailers are going to have different stylistic sort of preferences for things like clothing and things like that. So your certain problems are going to lend itself to off the shelf. Certain problems are going to lend itself to custom solutions. And so the answer is really it depends. Yeah, sure.
So have you taken this to the next step? Is there data that shows that process of using computer vision to make a recommendation
Yeah.
And they have ideas about doing this stuff. There's no one here that can program, but part of the gap was that it was that when it came that time to selling a solution to a store, whether it's a grocery outlet or a fashion store, at the time, this is only a year ago, there wasn't, or at least there wasn't being presented data that supported, that didn't mean, they understood the process, they didn't see the data that supported it as a
Yeah.
functional addition to the model.
Yeah, I don't know of a lot of data specifically for things like this in the retail space, but I will say that, like Netflix, what they're doing is they're building a vector that represents you, and they're building vectors that represents every single movie.
I'm questioning the technology.
Yeah, yeah.
In retail,
Sure.
we've seen
Yeah, I guess what I'm saying is that the techniques, have been shown to be very successful in other sort of industries. So I think, applying those techniques here could have a lot of benefit. If you have more specific.
Yeah, this
answer.
isn't all like future, like I said, 500 robots and one retailer being rolled out now. So these POCs didn't happen overnight. They were probably happening 3 years ago, right? And the fact that they're actually rolling out is kind of what I get excited about, and it's not just one retailer, it's two. Probably because it kind of comes down to out of stocks in this case in fast food consumable goods. It is a hundreds of billion-dollar problem that has not been solved by the industry or any one retailer effectively for decades. So those two retailers specifically have obviously vetted this out. I have to trust that they have before they made this huge investment. Those two are, yes. Yep.
I can see this being adopted more quickly in the grocery because the products are distinct and discreet. Someone's walking down the aisle, they always buy Quaker Oats, they want to get that coupon on their phone right before they get there to say, here's a store-brand Oats version. They know what they're picking off the shelf, they've got the moment, right?
Yeah.
But with fashion, I was curious because that seems...
Yeah, there's some, I think, at least from my experience, there's feelers going out, but I don't think that there's a lot of data quite yet.
Yeah, I would say on the fashion side, where it's actually taking hold actually isn't in store, it's more online, which is really the principle that Florian was kind of illustrating. Image search is pretty pervasive, and there are definitely retailers that are applying that from a search capability online. In store, it seems very experimental still with the magic mirrors and those kind of things from a fashion side, for sure.
Question about your first model, the semantic segmentation model
Uh-huh.
that you showed. So somebody had to sit and pixel level
Yeah.
label this data, right?
Right.
So if you don't mind me sharing with me, two questions really. How many label images have you got, and how long did it take for them to pixel level? Because I don't think there's any open image data set for retail or fashion.
This was an open data set. Yeah. There was in the tens of thousands of images, and it does take a while. To your point, in a more realistic example, we would typically build a tool to make the annotation faster, right? So like, let's say we would even bootstrap it with a model that can already sort of roughly generate the segmentations, and then we just have a human fine-tune them, and that greatly cuts down on the time that it takes to annotate a data set, right?
Pretty much what you're doing, but I was wondering
Yeah.
if somebody actually labeled it, you had an open data set.
Yeah, it was an open data set, but somebody did label it. Yeah, that's right.
I think we're
Anything
getting
else?
kicked
We're
out of the
getting
room.
kicked out of here, I think.
Thank you, everyone, for joining.